Hello and welcome to the second video on sequences. Now that we have an idea of what a sequence is, we want to be able to determine whether a sequence converges or diverges. Remember, a sequence converges if the terms of the sequence get very close to equaling some specific finite number as n gets large. This is called the limit of the sequence. A sequence diverges if its terms do not approach a specific finite number. As we'll see, we can often use what we already know about limits of functions from Calculus 1 to calculate limits of sequences. However, we'll also encounter some sequences that force us to develop new methods of taking limits. Here's what we plan on doing in this video. For each example, I'd recommend pausing the video once the problem is given and trying to work through it by yourself. If you find that you are stuck, unpause the video for a few seconds to give yourself a hint in the right direction. Let's first look at this example, the sequence whose terms are the natural log of the product n times sine of 1 over n. We want to know whether this sequence converges, and if it does, what its limit is. Pause the video here and see if you can answer this one already. The first thing to notice in this example is that we can replace all the n's with x's and consider the limit this way. This is due to the following theorem that says, if a function f of x has a limit L as x goes to infinity, then the sequence obtained by replacing all x's with n's must have the same limit L. It's important to note that f of x must have a limit or go to plus or minus infinity for this theorem to be guaranteed to work. For example, if f of x equals sine of pi times x, the limit of f of x as x goes to infinity does not exist. But the sequence whose nth term is sine of pi times n does converge. Try writing down a few terms of this sequence to determine what its limit is. Now that we've made this first step, we can use all of our previous knowledge of limits to calculate the limit of this sequence. In particular, we can use things like L'Hopital's rule, the limit laws, and the squeeze theorem when considering sequences. Whenever we are considering the limit of a function composition, remember we must first determine the limit of the inside function, and then use that to calculate the limit of the overall function. In other words, we should work from the inside out. So we'll start by calculating the limit of 1 over x as x goes to infinity. We've already determined that this limit is 0, which means that the limit of sine of 1 over x as x goes to infinity is equal to sine of 0, which is also 0. Of course, as x goes to infinity, x goes to infinity. So notice the inside of this larger function composition is of the form infinity times 0. This is what's known as an indeterminate form. In other words, we cannot determine this limit without doing more work. The way we usually deal with limits of indeterminate form is to use L'Hopital's rule. However, L'Hopital's rule only applies to indeterminate forms of the form 0 over 0 or infinity over infinity. Since multiplying by x is equal to dividing by 1 over x, we can rewrite our limit this way. Now that we have written this as 0 over 0, we can apply L'Hopital's rule, which says the limit of f of x over g of x is equal to the limit of f prime over g prime. Taking the derivatives of each and remembering to apply the chain rule, we get cosine of 1 over x times negative 1 over x squared in the numerator and negative 1 over x squared in the denominator. This simplifies to the limit of cosine of 1 over x as x goes to infinity, which is equal to cosine of 0, which is 1. Therefore, our overall limit is the natural log of 1. Recalling the behavior of natural log, the natural log of 1 is equal to 0, and therefore the sequence, natural log of the product of n times sine of 1 over n, converges to 0. One thing to note. Once we get comfortable working with sequences, there's no need to replace these n's with x's. We simply need to remember that n is our variable. Let's consider our next example, n factorial over 5 to the n. Remember that n factorial is equal to n times n minus 1 times n minus 2 all the way down to times 3 times 2 times 1. So for example, 4 factorial is equal to 4 times 3 times 2 times 1, which is 24. It's also worth noting that n plus 1 factorial is equal to n plus 1 times n factorial, which will come in handy in later sections. It should be clear that n factorial goes to infinity as n goes to infinity, as we keep multiplying by numbers that are growing larger and larger without any bound. Similarly, 5 to the n also goes to infinity. This is a geometric sequence where r equals 5. So again, we have an indeterminate form, this time infinity over infinity. Unfortunately, we can't apply L'Hopital's rule like we did in the last example. This is because n factorial is defined only for integers, and therefore we can't take its derivative. So we need to find another way to do this. It's tempting to look at the first few terms of our sequence and try to guess the limit from these. This is often a good starting point, but it can sometimes be misleading. This is because the limit of a sequence is determined by what happens as n gets very large, and not for relatively small values of n. The first few terms of this sequence are decreasing, so a first guess might be that its limit equals 0. This turns out to be wrong in this case, which we'll see by looking at the nth term in general for large values of n. Here we have n factorial over 5 to the n. Let's look at the nth term of the sequence when n is greater than 5. For each term of n factorial in the numerator, we have exactly 1 5 in the denominator. So we can write our terms like this. Now let's group these terms like so. Notice that the value in the middle parentheses is greater than 1, since each term in the numerator is greater than 5. So the terms of our sequence are greater than n over 5 times this other term. Multiplying this out, we get 24n over 3,125. Taking the limits of both sides, we see that this right-hand side diverges to infinity. Since the terms of our sequence are larger than the terms on the right-hand side, we can conclude that n factorial over 5 to the n also diverges to infinity. In this last example, we are just given the first few terms of our sequence, so we'll start by finding a formula for the nth term and go from there. The first thing to notice is that the terms alternate in sign, so an must have a negative 1 to the n in it, as negative 1 to the n is negative 1 when n is odd, and it's positive 1 when n is even. For the rest of the term, we're going to have to make some good guesses based on our observations. Except for a few terms, it looks like our numerator increases by 5 for each successive term. Following this idea, let's multiply the second and third terms by 5 over 5. The idea is to rewrite them so that they fit the pattern we've observed for the other terms. Now we see that this pattern does hold for all the given terms, so we can say that the numerator for this sequence is 5n. Lastly, we have the denominator. It doesn't follow quite as nice a pattern, but if we subtract 1 from each number in the denominator, we get 1, 4, 9, 16, 25, and 36. This pattern should be familiar, as it is n squared. Therefore, the formula for the terms of this sequence is negative 1 to the n times 5n over the quantity n squared plus 1. Now that we have the formula, we can try to find the limit. This negative 1 to the n is kind of troublesome, but we can deal with it using the following theorem. This theorem says that the limit of a sequence an is equal to 0 if and only if the limit of the absolute value of an is equal to 0. It's important to note that this theorem only works for the limit 0. You should try to find an example of a sequence where the theorem fails if we replace 0 with another value. In this case, however, the theorem gives us what we're looking for. Taking the absolute value of these terms, we can now evaluate this limit using Calculus 1 techniques. We could use L'Hopital's rule again, but that would be overkill. In general, to find the limit of a rational function, divide each term by the largest power of n that appears in the denominator. In this case, n squared. Simplifying and then taking the limit of this equivalent expression, we get 0 over 1 plus 0. Applying our theorem, this tells us that the given sequence converges to 0. As a side note, what would have happened if we instead had the sequence negative 1 to the n times 5n all over the quantity n plus 1? The limit of this sequence does not exist. Try to explain why. Here are a few similar examples for you to try on your own. The answers to these will be posted online. Let's stop here for now. In this video, we saw some ways that we can find the limit of a sequence. We'll often use previous techniques like L'Hopital's rule, our limit laws, and the squeeze theorem. But sequences occasionally need new theorems and new definitions, like the ones we saw in the last two examples.